Hello everyone, welcome to this edition of my Bioinstruments subjects. Today we want to take a look at understanding immunoassays, and in the following slides we will see a comprehensive equipment guide. This presentation provides an in-depth guide to immunoassay equipment, techniques, and applications in modern laboratory settings. Immunoassay represent a comprehensive technology in clinical diagnostics, research, and pharmaceutical development. We will explore key components including assay plates, microplates, design features, automated analyzers, semi-automated systems, and commercial kit selection. Each component plays a critical role in achieving accurate, reliable, and efficient testing results. The goal is to enhance understanding of equipment functionality, optimize implementation strategies, and provide practical knowledge for troubleshooting common issues. We'll also examine quality control measures, standardization protocols, and emerging trends that are shaping the future of immunoassay technology. Okay, let's go. Okay, let's take a look at evolution of immunoassay technology from manual to automated. Manual assays, I should say that early immunoassays were labor intensive and time consuming procedures that required skilled laboratory technicians, and they relied on manual procedures, including precise pipetting, sample preparation, washing steps, and visual interpretation of results. Uh, Therefore, technicians performed each step of the process from sample addition to incubation timing, washing, and result documentation. Um, these methods were prone to human error, had limited uh, throughput capacity, and showed significant operator to operator variability. Despite limitations, manual methods established fundamental principles and remained viable for low volume or specialized testing. And automated systems that we can see its notes here. Automated systems, automation increased efficiently and precision through computerized control systems and robotic handling mechanisms. Analyzers handle multiple steps simultaneously, including precise reagent dispensing, timed incubations, washing cycles, and signal detections. Results are consistent and reliable with the reduced coefficients of variation and high reproducibility across different testing conditions. Modern systems incorporate barcode tracking, automated quality control, data management, and integration with laboratory information systems. High throughput capabilities enable processing hundreds of samples per hour while maintaining precision and minimizing hands on time for laboratory personnel. Key components of immunoassay testing systems. Modern immunoassay systems consist of three critical components: a specialized microplates for sample reactions, automated analyzers for detection and processing, and finally, validated reagent kits containing calibrated materials essential for accurate testing. Okay, let's see each of them in a separate way. Okay, number one is assay plates. Polystyrene or polypropylene microplates with 96 or 384 wells, surface treated to optimize protein binding and signal to noise ratios. Number two are analyzers. Incorporate optical detection systems, absorbance, fluorescence, or chemiluminescence, feature automated liquid handling, incubation control, and data processing capabilities. And number three is immunoassay kits, contain calibrated antibodies, detection reagents, buffers, and reference standards, include validated protocols for a specific analytes with defined sensitivity and detection ranges. Okay, let's see assay plates and their types and applications. Laboratory assay plates are essential components that directly influence immunoassay performance, sensitivity, and reproducibility. Selection should be based on specific application requirements. Here are three parts for that. The first ones are microplates. Common in high throughput screening and automated systems available in 6, 12, 24, 96, 384, and 1536 well formats. Materials include polystyrene, polypropylene, and cycloolefin polymers. Clear, white, or black options optimize different detection methods. The second ones are ELISA plates. They are designed for enzyme-like immunosorbent assays, optimize antibody-antigen interactions through enhanced protein binding, feature treated surfaces for improved molecule attachment, available with high binding or medium binding capacities for different assay requirements. And the last ones are specialty plates, customized for specific assay types and detection methods. Modified surfaces for unique applications like cell-based assays include um, streptavidin-coated poly-D-lysine and other functionalized surfaces. Filter bottom plates allow for multiplexed wash steps and vacuum filtration. Um, there are also other plates like strip well plates, and they are individual strips of 8 or 12 wells that can be separated as needed. They reduce waste when running partial plates, and also other things that can be mentioned in um, more precise slides in the future. Okay, let's see microplate design, features, and material selection. The physical and chemical properties of microplates directly impact assay performance, reproducibility, and sensitivity. Optimal design requires careful consideration of multiple factors. Here are the factors. Number one is well geometry, affects reagent mixing and signal detection. Round wells promote uniform mixing, while flat bottom wells maximize optical path length for absorbance readings. V bottom wells enhance sample recovery and are ideal for um, precipitation assays. Well depth to width ratio influences evaporation rates and edge effects. The second factor is material selection, influences chemical capability and background signal. Polystyrene offers excellent optical clarity for colorimetric assays, but may bind proteins non-specifically. Polypropylene resists organic solvents and reduces protein binding. COC, as we know as cyclic olefin copolymer, provides superior optical properties for fluorescence and luminescence applications with minimal autofluorescence. And the last part is surface properties. In surface properties, it is obvious that they impact binding efficiency and specificity of biomolecules. High binding surfaces use hydrophobic and or charge modifications to enhance protein attachment. Low binding surfaces minimize non-specific interactions for cell-based assays. Specialized coatings like uh, streptavidin, polylysine, or collagen create functionalized surfaces for targeted applications and can dramatically improve signal to noise ratios. Modern microplates manufacturing techniques allow for customization of these features to match the specific assay requirements. Selection should be guided uh, assay type, detection method, and target analysis. Okay, optimizing well geometry and surface treatment. Let's see what this is. The physical characteristics of microplate wells significantly impact assay performance, reproducibility, and sensitivity. Optimizing these parameters ensures consistent binding kinetics and improved signal to noise ratios. Okay, let's see the subtitles. Well shape. Round wells provide uniform fluid dynamics and even distribution of reagents. Square wells maximize surface area and accommodate larger sample volumes. V-shaped bottom and U-shaped bottom designs facilitate the plating and minimize dead volume. The shape selection impacts mixing efficiency, binding kinetics, and light scattering properties. The second part is about surface coating. Enhance binding specificity and reduce non-specific interactions. Options include hydrophilic, hydrophobic, or charged surfaces. Common treatments: polylysine for cellular assays, streptavidin for biotinylated molecules, and carboxyl groups for covalent protein coupling. Surface modifications affect protein orientation and accessibility of binding sites. And the last one is volume capacity. Match assay needs with appropriate well dimensions. Standard 96 well plates typically accommodate 100 to 200 microliters, while 384 well plates handle 20 to 50 microliter per well. Miniaturized 1536 1536 well formats work for 2 to 10 microliter volumes. Volume uniformity across well is critical for assay reproducibility and reagent conservation in high throughput screening applications. Other important considerations include optical clarity for detection systems, plate rigidity to prevent wrapping during temperature changes, and compatibility with automation equipment. Manufacturers now offer specialized surface treatments optimized for specific assay types. And now let's see modern immunoassay analyzers. What are the core technologies? Modern immunoassay analyzers integrate several sophisticated technologies to deliver precise, reliable, and efficient diagnostic results. These core components work in harmony to automate complex immunological testing procedures. The first one is optical detection. Let's see it here. What is it? It utilizes advanced spectrophotometry, fluorescence, and chemiluminescence to measure signal intensity with high sensitivity. These systems can detect minimal concentrations of target analytes through precise wavelength discrimination and signal amplification. The second one, let's see it here. Okay. The second one is fluid handling. Employs precision pumps, valves, and microfluidic technologies to accurately dispense, mix, and transport samples and reagents. These systems control volumes from microliters to milliliters with minimal cross contamination risk. And the third and last one is robotics. Robotics integrates mechanical components with sophisticated motion control systems to automate sample loading, plate handling, and incubation steps. Modern systems feature multi-axis movement with position accuracy within micrometers or other features for these robotics um, facilities that we have. Each of these technologies has evolved significantly over the past decade, enabling higher throughput, improved precision, and reduced operator intervention. The integration of these components, controlled by sophisticated software algorithms, has transformed laboratory workflows and expanded diagnostic capabilities. Okay, look at this table below. This table is a comparison between the automated and semi-automated systems here. There are three features that this comparison has been done. The features are throughput, labor, and cost. That we know that automated throughput high, labor low, cost high, and semi-automated medium, moderate, and you can see all the comparisons here. Quality control in immunoassay equipment. It has three parts. Calibration, which is, we should say that regular calibration ensures accurate measurements and reliable results. Includes verification with standard reference materials and adjustments of detection systems. The second one is maintenance. A scheduled preventive maintenance extends equipment lifespan and prevents downtime. Includes cleaning, component inspection, and replacement of worn parts. The third one is validation. Comprehensive validation confirms system performance, meets a specification, include precision testing, linearity assessment, and comparison with reference methods. Effective quality control processes are essential for maintaining the reliability and accuracy of immunoassay equipment. These three interconnected steps form the foundation of a robust QC program that ensures consistent results and regulatory compliance. Laboratory managers should establish commercial immunoassay kits selection criteria. When selecting commercial immunoassay kits for your laboratory, several critical factors should be evaluated to ensure optimal performance and reliability. The following criteria represent the most important considerations that will impact your testing outcomes and overall efficiency. Number one is specificity, the ability to detect only the target analyte with minimal cross-reactivity to similar compounds. High specificity reduces false positive and ensures the assay measures exactly what you intend to measure. Number two is sensitivity, the lowest concentration of analyte that can be reliably detected. Higher sensitivity allows for detection of trace amounts, critical in applications like early disease diagnosis or environmental monitoring. And the third one is accuracy. Accuracy is about the closeness of measured results to the true value. Accurate kits produce consistent, trustworthy results across multiple tests and different laboratory conditions, supporting confident clinical or research decisions. Additional factors to consider include precision, which is reproducibility of results, range, a span of concentration, span of concentrations that can be measured, a stability, that is shelf life and reagent durability, value. Value is the last one. Value is the cost relative or to performance. These are other factors that must be mentioned. And always evaluate manufacturer validation data and peer-reviewed literature when making your selection. Now let's see standardization and calibration protocols and what are they about. Proper standardization and calibration are essential for accurate immunoassay results. Following these protocols ensures consistency across multiple test runs and different laboratory environments. Number one is preparing standards. Preparing is about creating a series of calibrators with known concentrations that span the expected range of patient samples. Use certified reference materials, um, especially when available, to ensure traceability to international standards. Number two is running these calibrators. The processing calibrators through the immunoassay system under the same conditions as patient samples. This establishes the relationship between analyte concentration and signal intensity for the specific assay run. Number three is verifying these results. Run quality control samples with predetermined acceptable ranges to validate calibration curve. If QC results fall outside acceptable ranges, troubleshoot and repeat calibration as necessary. Okay, these are the three main parts in standardization and calibration protocols. There are also other sections that we can talk about. For example, we can generate calibration curve. That's a plot, measured signals against known concentrations to create a calibration curve. And modern analyzers automatically generate this curve using appropriate mathematical models like linear, logistic, etc. And number five is scheduling recalibration. Establish routine calibration schedules based on manufacturer recommendations, regulatory requirements, and observed drift in system performance. Document all calibration activities for regulatory compliance. Consistent adherence to these standardization and calibration protocols helps minimize analytical variability and ensures reliable patient results across different testing scenarios. Okay, let's see some charts about troubleshooting common equipment issues. Um, the bar chart above shows the relative frequency of common problems encountered in immunoassay equipment. Understanding these issues is essential for maintaining laboratory efficiency. The first one is about no signal, the most common issue. This problem occurs when the detection system fails to register any reaction. Common causes here include reagent degradation or expiration, improper sample preparation, detection system malfunction, or incorrect incubation temperature or time. The second bar is about high background noise. High background noise makes it difficult to distinguish true positive results from interference. This typically stems from number one, insufficient washing between steps, number two, cross reactivity with non target molecules, number three, contaminated reagents or equipment, and number four, non-specific binding to assay surfaces. And the last bar is about inconsistent readings. Variability between replicates undermines result reliability. Contributing factors include pipetting errors or inconsistency, temperature fluctuations during the assay, uneven plate coating or well-to-well variability, calibration drift in optical detection systems, implementing regular maintenance schedules, proper staff training, and standardized protocols can significantly reduce the frequency of these common equipment issues and improve overall assay reliability. Okay, miniaturization, um, biosensors, and AI integration. These are the three future trends in immunoassay technology. Let's see the first one, miniaturization. Miniaturization, for example, suppose we have a lab on a cheap technology that can easily reduce immunoassay systems to handheld devices, or microfluidic platforms enabling point of care testing with sample volumes under 10 microliters, or, for example, portable analyzers allowing field deployment in resource limited settings. These are really great. Um, the second trend that may happen and will happen, we know that, are biosensors, electrochemical and optical biosensors enabling continuous analyte monitoring, surface plasmon resonance SPR technology, providing labeled-free real-time detection, and also nanomaterial enhanced biosensors improving sensitivity to femtometer concentrations. That's great. And the last one are, as we see here, AI integration. Okay, machine learning algorithms, automating result interpretation, and reducing false positives are the main features for AI integration. Predictive analytics, identifying testing anomalies before equipment failure. These are all what AI can do for us in the future. And also neural network optimizing assay parameters for unprecedented sensitivity and specificity. Okay, these are three main future trends that may happen, and as we believe they will happen. Let's see cost analysis and ROI considerations. Cost analysis, we have three main issues in cost analysis, which are savings, efficiency, and investment. And They don't need any other interpretation. And as it is said here, a thorough cost analysis informs purchasing decisions, and also ROI considerations justify investments. That's all for this slide. Now let's see best practices and implementation guidelines. Now, implementing robust protocols ensures reliable and reproducible immunoassay results. The following guidelines help laboratories establish effective practices for optimal performance and compliance. Let's see training. Training is about ensuring staff proficiency through comprehensive initial training and ongoing education. Include hands-on practice with equipment, troubleshooting scenarios, and regular competency assessments. Consider manufacturer provided training programs for specialized instruments. The second one is maintenance. Regular equipment checks are essential for reliable operation. Implement daily, weekly, and monthly maintenance schedules following manufacturer recommendations. Document all maintenance activities, calibrations, and repairs to ensure traceability and compliance. And the last one is documentation. Documentation is about maintaining detailed records of all procedures, results, and quality control measures. Establish standardized forms and electronic systems for consistent documentation. Include batch information, reagent details, calibration data, and any deviations from standard protocols. Um, Other outlines that we can name are validation and quality control. Consider applications of these best practices support regularity, compliance, and ensures the generation of high quality, reliable immunoassay data for clinical or research applications. Thank you all for your attention. Today's topic about immunoassays come to an end here. I hope you enjoyed it. Until the next lesson, goodbye and take care.